Hello students, as we are discussing chapter structure of atom and atomic models, and we have discussed about the limitations of Rutherford's model as well, and later on we discussed how various developments led to the development of Bohr's model. And actually two main developments that were taking place that time. First, we had discussed about dual nature of electromagnetic radiation. That means radiations have wave-like nature as well as particulate nature. And next important development was in spectroscopy, that is atomic spectra. And when atomic spectra were taken for various different elements, they showed that there exist certain specific energy levels in an atom. That led to the main development of Bohr's model. So firstly, we'll discuss what is atomic spectra. As you know that light travels at a constant speed through vacuum, that is 3 multiplied by 10 raised to the power 8 meter per second. But when light enters in a different medium, then the speed gets the speeds gets changed, and it depends on the nature of the material through which the light is traveling. And when light travels through a prism, you know that prism deviates the various colors present in the white light. As we all know that white light is made up of 7 colors. So this deviation of path of the light while passing through the prism helps to disperse light in 7 colors, and we get a kind of spectrum of a band of 7 colors in a specific sequence, in which you can see that blue color is deviated the most, whereas the red color with longest wavelength deviates least. So we obtain this spectrum in the form of a band of 7 colors, and as you can see that these 7 colors are merged into each other, means there is no empty space you can see. एक दूसरे में merge हुए में है, continuity है colors की. तो this kind of spectrum in which there is a continuity of colors is called a continuous spectrum. तो white light या किसी भी source से जो white light अगर हमें obtain होती है, whether it is sun or some other artificially made sources, they all give this kind of continuous spectrum. And in this spectrum, definite band of 7 colors in this sequence of Vibgyor is obtained. But what happens when we heat a particular substance? Like अगर हम matter की बात करें, तो when we heat a particular substance or we pass through a kind of white light or other kind of light through this sample of any matter, then what happens? Certain electrons, they actually acquire energy and they get excited to certain higher energy levels. Actually, there exist certain energy levels in the structure of atom that we'll discuss in Bohr's model. That actually given was after the discoveries of atomic spectroscopy. And then when electrons get excited to higher energy level, तो वो एनर्जी लेवल जो एक्साइटेड स्टेट होता है किसी भी इलेक्ट्रॉन का, वो उतना स्टेबल नहीं होता उस एटम के लिए. तो दे रेडिली जंप बैक टू द नॉर्मल एनर्जी स्टेट विच इज़ कॉल्ड द ग्राउंड एनर्जी स्टेट. तो इस जंप में एटम्स और इलेक्ट्रॉन्स जो एनर्जी एब्जॉर्ब करके वो एक्साइट हुए होते हैं, उस एनर्जी को वो एमिट कर देते हैं. एंड दिस एमिटेड एनर्जी, if it is passed through a prism or it is analyzed under a spectroscope, this gives a specific lines in a spectrum, and these lines have a specific wavelength which is characteristics of any kind of element. So these kind of spectrum are called atomic spectrum, and atomic spectra are actually discontinuous, as you can see here in the diagram, because they do not emit the entire wavelength which a white light consists of. Rather, they show specific lines for specific wavelength or frequency, and these lines appear discontinuously because there are certain gaps in between these lines, as you can see. So these kind of spectrum are called discontinuous spectra, and this is contrary to that light spectrum. Light का जो spectrum है वो continuous होता है, this is a kind of discontinuous spectrum. And these atomic spectra are of two types, emission and absorption spectra. Let us discuss them in detail. What is an emission spectra? As the word emission means, when the light or when the specific radiation is emitted from an matter, from a kind of matter, and when it is analyzed under spectroscope, then the kind of spectrum obtained is called emission spectrum. Now, when a particular sample of matter will emit radiation, if we pass electric discharge through a gas or we heat a substance at very high temperature, at that time the atom acquires an excited state, and from where when it returns back to the normal state, then it emits certain radiation, and these radiations, when analyzed under spectroscope, they give a kind of specific lines of specific wavelength in a dark colored spectrum. So here you can see that as it is a kind of discontinuous spectrum, this is also called as line spectrum because it observes as a manner of certain lines of specific wavelength. And you know that these line spectra are very important for a particular element. जैसे हमारे fingerprints, किसी भी ह्यूमन बीइंग के फिंगरप्रिंट उसकी एक स्पेसिफिक कैरेक्टरिस्टिक प्रॉपर्टी है. सिमिलरली हर एक एलिमेंट के एमिशन स्पेक्ट्रा या लाइन स्पेक्ट्रा उसका कैरेक्टरिस्टिक प्रॉपर्टी होता है. तो दीज आर जस्ट लाइक द फिंगरप्रिंट्स ऑफ एटम्स. नेक्स्ट इज एब्जॉर्प्शन स्पेक्ट्रा. जस्ट रिवर्स, वहाँ एमिटेड लाइट एमिटेड रेडिएशन का स्पेक्ट्रोस्कोपी पे एनालाइज करते हैं, वेयर एज हेयर in absorption spectrum, when a continuous electromagnetic radiation, और you can say जब एक white light किसी आप source में से pass through करते हो, किसी matter में से, किसी gas के cloud से या किसी solution किसी salt के solution में से अगर आप white light को pass करते हो, then कुछ amount में light जो है वो उस matter के through absorb हो जाती है to get the electron excited, और जितनी एनर्जी वो एब्जॉर्ब कर चुके हैं, अब बाकी की जो लाइट उस मैटर के थ्रू ट्रांसमिट हो रही है या वहाँ से पास आउट हो रही है, इफ इट इज ऑब्जर्व्ड इन अ स्पेक्ट्रोस्कोप, देन व्हाट विल यू ऑब्जर्व? ऑब्वियसली कुछ अमाउंट में लाइट जो उस मैटर ने एब्जॉर्ब कर ली वो अब स्पेक्ट्रम में आपको नहीं मिलेगी. तो यू विल गेट ऑल दोज स्पेसेस एज अ ब्लैंक डार्क स्पेस when what wavelength or frequency is absorbed by the matter. So here you can see that white light आपने उस source में से source में से जो white light pass हो रही emit हो रही है, that is passed through a sample of matter, whether it is a gaseous sample or solution of a salt. Then बची हुई जो light को आपने जब observe किया, तो you can find here, otherwise ये उसी तरह का विबग्योर पैटर्न वाला स्पेक्ट्रम होता है, बट इट इज नॉट नाउ कॉन्टिन्यूस बिकॉज सम अमाउंट ऑफ रेडिएशन इज एब्जॉर्ब्ड बाय द सैंपल. तो वहाँ जहाँ जहाँ एब्जॉर्प्शन हुआ है उस जगह पे आपको डार्क लाइंस नजर आ रही हैं. तो इट कंसिस्ट ऑफ डार्क लाइंस इन अदरवाइज कॉन्टिन्यूस स्पेक्ट्रम, और ये डार्क लाइंस उसी जगह पे आती हैं जहाँ पर उसी पर्टिकुलर सब्सटेंस के एमिशन स्पेक्ट्रम में कलर्ड लाइंस मिलती हैं. बिकॉज ऑब्वियसली जितना अमाउंट में रेडिएशन एक सब्सटेंस एब्जॉर्ब करता है फॉर एक्साइटेशन, तो वो वापस रिटर्न आने पर एमिट भी वही रेडिएशंस करेगा. तो डार्क लाइंस आर कॉरेस्पॉन्डिंग टू द रेडिएशन एब्जॉर्ब्ड बाय द सब्सटेंस फ्रॉम वाइट लाइट. ओके, तो दैट इज व्हाई वी अपीयर दीज डार्क लाइंस इन अदरवाइज कॉन्टिन्यूस स्पेक्ट्रम. तो दोनों में क्या डिफरेंस हुआ? एमिशन स्पेक्ट्रम कंसिस्ट ऑफ colored lines only, they are separated by certain gaps, whereas in absorption spectrum we obtain dark lines corresponding to the radiation absorbed by the substance, और बाकी का आपको same discontinuous way में normal spectrum मिलेगा. Next we can see have a quick recap of these three types of spectrum. For example, if you passing white light emitting from any source or a black body, because it emits all radiation, तो प्रिज्म में से पास करने पे आपको इस तरह का continuous spectrum मिलेगा consisting of all 7 colors without any gap. Whereas if we see the emission spectrum, we get only those colored lines which radiations are emitted by a particular substance or a gas. और absorption spectrum के अंदर हमें यही specific लाइंस जो एमिशन स्पेक्ट्रम में मिलती हैं सेम, अगर आपने सब्सटेंस का एब्जॉर्प्शन स्पेक्ट्रम स्टडी करना है, यू विल फाइंड द डार्क लाइंस इन दैट पर्टिकुलर कॉन्टिन्यूस स्पेक्ट्रम. मतलब कॉन्टिन्यूस स्पेक्ट्रम अब कॉन्टिन्यूस नहीं रह रहा, क्योंकि वो है तो वाइट लाइट का ही, बट उसमें से कुछ लाइंस जो गायब हुई हैं, जो डार्क लाइंस शो हो रही हैं, दे आर एब्जॉर्ब्ड बाय दैट पर्टिकुलर substance. So this is how we get different types of emission and absorption spectrum for a particular substance. Next, it's very important because it was the hydrogen atom for which the emission spectrum was studied first. And emission spectrum of hydrogen consists of large number of various lines which were related to specific wavelength. And some of these lines are found in visible region while others are in ultraviolet or IR, infrared region. In 1885, Balmer developed a relationship among the wavelengths of lines obtained in visible region, and he named that series of lines. As you can see here in this diagram, these black colored lines are obtained in visible region. और ये सबसे पहले Balmer ने इनको स्टडी किया, and these series of lines were named after him as Balmer series. Later on, other lines जो UV और IR region में थी, उनको भी अलग अलग साइंटिस्ट ने डिस्कवर किया, and these series are named after their discoverers. So these series, as they were discovered by different scientists, so they are now, you can have a look what are the names used for these particular lines. First series is Lyman series, which is obtained in ultraviolet region. Second is Balmer series, which is obtained in visible region. Third, fourth and fifth, which are obtained in IR region, are named as Paschen series, Brackett series and Fund series. And during the same time, Rydberg was also working on this relationship between these lines, and he gave an equation for calculating wavelength and wave number for a particular specific line which we obtain in emission spectrum of hydrogen. And for hydrogen, he gave the formula 1 over lambda, or you can say 1 over lambda is equal to wave number. So wave number of any spectral line is equal to RH 1 over n1 square minus 1 over n2 square. Here this RH is actually Rydberg's constant, and its value is 109677 centimeter inverse, or in meter 1.09677 10 raised to the power 7 per meter. And N1 here is, it's very important to understand what is N1 and what is N2. N1 is 1 for Lyman series. N1 is 2 for Balmer series. It is 3 for Paschen, 4 for Brackett and 5 for Fund. And N2 will be greater than N1. मतलब ये एक्चुअली N2 और N1 ये बता रही है कि इलेक्ट्रॉनिक जंप कहाँ से कहाँ हुआ है. As emission spectrum obtains only when electron jumps from higher to lower energy level. तो N1 हमने फिक्स कर लिया हर एक सीरीज के लिए, लाइमन, बामर, पास्चन, ब्रैकेट, फंड में. तो वो लेवल, एनर्जी लेवल है N1 जिस पर इलेक्ट्रॉन फाइनली जंप करके पहुंचता है. दैट इज द ग्राउंड स्टेट. तो ग्राउंड स्टेट इज फर्स्ट एनर्जी लेवल फॉर लाइमन. बामर के लिए ये 2 होता है, पास्चन के लिए 3 होता है, ब्रैकेट के लिए 4 एंड फंड के लिए 5. अब N2 मतलब हायर एनर्जी लेवल जिससे इलेक्ट्रॉन ने जंप किया है, तो वो कोई भी हायर एनर्जी लेवल हो सकता है. तो इट कैन हैव वैल्यूज N1 plus 1, N1 plus 2, N1 plus 3 or so on up to infinity it may be. Let us see how to fix the values of N1 and N2 while looking at these transition series. For example, Lyman series, you can say Lyman series में मैंने आपको बताया ग्राउंड स्टेट होता है फर्स्ट एनर्जी लेवल, जिसके लिए N1 की वैल्यू आपने 1 रखनी है. तो फॉर Lyman series N1 is 1. अब इस N1 तक इलेक्ट्रॉन कहाँ से जंप करके आ सकता है? स्टार्टिंग फ्रॉम द हाईएस्ट, यू कैन से इन्फिनिटी से इलेक्ट्रॉन ने जंप किया, एंड इट jumps to the lowest energy level 1, तब n2 की वैल्यू infinity होगी and n1 would be 1, and this line is called limiting line. और उसके अलावा बाकी की जो लाइंस हैं, फॉर एग्जाम्पल इफ इलेक्ट्रॉन जम्प्स फ्रॉम सेकेंड लेवल n is equal to 2 to n is equal to 1, then that line is called first spectral line. अगर इलेक्ट्रॉन n is equal to 3 से n1 पे जंप करता, then it is called second spectral line. Similarly, you can say it can n2 can have value 2, 3, 4, 5, 6, 7, so on up to infinity for Lyman series. Similarly, for Balmer series, you can say the lowest energy level up to which the electron jumps, जिसकी line आपको visible spectrum में appear होगी, that will be 2. तो n1 will be 2 for Balmer series, it is fixed. अब higher energy level n2 की value स्टार्टिंग फ्रॉम फर्स्ट लाइन के लिए वो 3 होगी, सेकंड के लिए 4 होगी, थर्ड लाइन के लिए 5 होगी, और लिमिटिंग लाइन के लिए ऑब्वियसली इन्फिनिटी. तो लिमिटिंग लाइन के लिए अगर आपको वेवलेंथ या वेव नंबर कैलकुलेट करना है, यू नीड टू पुट n2 एज इन्फिनिटी इन दैट रिडबर्ग इक्वेशन. सिमिलरली फॉर पास्चन सीरीज n1 इज इक्वल टू 3, मतलब पास्चन सीरीज नियर इंफ्रारेड में तब ऑब्जर्व होती है जब इलेक्ट्रॉन किसी भी हायर एनर्जी लेवल से थर्ड एनर्जी लेवल पे जंप करता है. तो दिस हायर एनर्जी लेवल कैन बी एनी वेयर फ्रॉम इन्फिनिटी, और उसके बाद फर्स्ट लाइन तब आएगी जब n2 आप पुट करोगे 3 + 1 4, और पास्चन सीरीज के लिए n2 5 होगा अगर सेकेंड लाइन की आप बात कर रहे हैं. सिमिलरली फॉर द ब्रैकेट एंड फंड सीरीज. So as we have discussed Rydberg equation for hydrogen atom, similarly Rydberg equation can also be used for other species that form hydrogen-like ions like helium ion and lithium ion. Just you need to use one more factor, that is Z square, in this equation, as you can see here, and Z is the atomic number of that particular element. For helium it would be 2 and for lithium it would be 3. Next, we can have some examples how to solve numericals on the basis of Rydberg formula. So in this question, spectral line corresponding to n1 3, n2 5. Calculate the wavelength and frequency of this spectral line, and to which spectral series does this line belong? In which region of electromagnetic spectrum will this line fall? So you need to give answers to these three things. Firstly, we will calculate wavelength from the Rydberg equation. And here you put value n1 and n2 as given in the question 3 and 5, and the answer would be 1282 nanometer, or in meter you can give answer in meter also, 1282 multiplied by 10 raised to the minus 9 meter. Now the second part of the question is frequency to calculate. Let us see, frequency is related to wavelength by this formula. C is equal to nu lambda and nu is equal to C over lambda. By putting the value of C, you can find the frequency 2.34 10 raised to the power 14 per second. Now the second question, to which spectral series does this line belong? ये इसका आंसर आपको मिलेगा n1 की वैल्यू चेक करके. n1 is 3, तो n1 1 is for Lyman series, 2 is for Balmer series, 3 is for Paschen series. So here this line belongs to Paschen series. And thirdly, the question is in which region, as we have already discussed that Lyman series obtains in ultraviolet, उसके बाद Balmer visible में, और बाकी IR में आती. तो this spectral line will fall in infrared region. So this is how you can solve questions. Let us have one more example. Calculate the wave number for the longest wavelength transition in the Balmer series of atomic hydrogen. Hydrogen atom के लॉन्गेस्ट वेवलेंथ ट्रांजिशन बामर सीरीज के लिए निकालनी है. लॉन्गेस्ट वेवलेंथ ट्रांजिशन का मतलब होता है जिस लॉन्गेस्ट वेवलेंथ तब आती है जब ट्रांजिशन सबसे छोटा हो, मतलब स्मॉलेस्ट ट्रांजिशन विल गिव यू द लॉन्गेस्ट वेवलेंथ. तो हेयर यू विल यूज द सेम Rydberg formula and R value you know. For calculating answers directly in meter, you can also use the value of Rydberg constant in meter. And n1 for Balmer series will be 2, and longest wavelength transition होती है सबसे छोटी transition, always remember that. And that is for that n2 will be have 3 value. तो N12 and N23 पुट करके आप सॉल्व कर लीजिए एंड यू कैन गेट द आंसर 1.523 10⁻⁶ मीटर इनवर्स इज द वेव नंबर ऑफ longest wavelength transition. I think I hope everything is clear to you all now. Thank you. Have a nice day.